In this lesson, we shall focus on chemistry, rates of reactions, grade 12. It's a revision, and we shall look at past exam questions on rates of reactions and rated questions. Right, first things first, we shall start by looking at question 5. Ordinarily and normally, questions must be started on a new page, and you need to consider the following decomposition reaction that takes place in a sealed 2 cubic decimeter container. Right, so you have here your nitrogen pentoxide, which actually undergoes decomposition into nitrogen dioxide and oxygen. The graph below shows how the concentrations of the dinitrogen pentoxide and nitrogen oxide change with time. Refer to the graph above and give a reason why Fa represents the change in the concentration of NO2 gas. Right, so first things first, we shall refer to the graph above. I'm going to show the graph now, but we shall refer to the graph and give a reason why A represents the change in the concentration of NO2. Now, a couple of things we need to obviously take into account in this particular question. It is the fact that you actually have been given this particular reaction, this one here. So you have that N2O5 breaks down into NO2 and oxygen. Right, so you have that your N2O5 breaks down into NO2 and oxygen. Okay, but also note that it is 2-4-1. Right, we have the 2-4-1 mole ratio, yeah? Now, this is the chemical reaction, and here's the graph. And if this is the graph, you're able to see what is happening to the graph here. There is this graph that begins from 200 and goes down to as close as possible to 50, but does not reach 50. This other graph begins from the, so this one is graph B. There's graph A that starts from the origin, and it shows an increase just above 250 and below 300. It's graph A. Okay. And the question is, refer to the graph and give a reason why A represents the change in the concentration of NO2. Why is it that A represents a change in the concentration of NO2 where NO2 is a product? Okay, they're telling us that A represents a change in the concentration of NO2. But we can see that NO2 is indeed a what? It is indeed a product. But we need to give a reason why A represents a change in the what? A change in the concentration. So the couple of things that are very important, but it is the fact that in the beginning, we're able to see that we have the vertical axis is the concentration axis, and the horizontal axis is the time axis. Now we can see that the initial concentration is 0, 0. Graph A starts from the origin, meaning in the beginning, we did not have the NO2. We did not have anything in terms of the products, of course, and therefore that would be the giveaway there. That would be the giveaway there. And so the reason would therefore be that the initial concentration, like we've seen, the initial concentration is only 0, right, of the NO2 gas, nitrogen dioxide gas. Simultaneously, somebody can say, if you don't want to say this, you can say that the concentration. Okay, y'all, let me check your question now. Okay, that's a good question. Which paper is this? I'll just check. Just 1 second. I'll check. I'll let you know. It is just 1 minute. I'll check for you. I'll let you know which paper this is. Right. So now I'll let you know what paper this is. Okay, yeah, it is June 2023. It is June 2023. Okay. All right, now. Right, June 2023. Right. So now we're looking at the fact that the initial concentration is 0. Okay, we can see that indeed the initial concentration here is 0 for cave A, and that is indicative of the fact that obviously we did not have anything of this substance, and it is the NO2 that it did not have. It is one of the products there, and that is the reason. So the way you would answer that question in the exam would be that the initial concentration is 0 of NO2. Simultaneously, you then say, alternatively, right, you then say, for example, or the concentration, right, you'd say the concentration increases, right, you can say the concentration increases. Alternatively, you can say the concentration does what? The concentration increases. In view of the graph, we can see that indeed the concentration of cave A increases, whereas the concentration, because this vertical axis is the concentration axis, we're able to see therefore the concentration of graph B decreases and the concentration of graph A increases. Okay, we're good. Next, consider the statement below. The rate of decomposition of the dinitrogen pentoxide is half the rate of formation of NO2. Okay. The rate of decomposition of N2O5. The rate of decomposition of N2O5 is half the rate of formation. We can see indeed by looking at the balanced chemical equation. Is it balanced? Okay, let's check if it's balanced. 2 times 2 is 4. We're 4 nitrogen atoms on the left, and here we're 4 nitrogen atoms on the right. How many oxygen atoms? 2 times 5 is 10 oxygen atoms on the left, and we're 4 times 2, which is 8 oxygen atoms on the left, plus 2 oxygen atoms, giving us 10 oxygen atoms. Indeed, you have 10 oxygen atoms, and obviously there's a balance in the atoms on both sides of the equations. Okay, right, now, the question is, the rate of decomposition of N2O5 is half. Okay, you can see the rate of decomposition of this is half the rate of formation of NO2. Because you can see if this one is 2, this is 4. So this one is half of this. Is this statement true or false? Give a reason for your answer. Is this true or false? Give a reason for your answer. I mean, by merely looking at this, we're able to look at this and see that indeed it is true. Right? Why would this be true? N mole of N2O5 forms 2N mole. Can write 2N mole even without the E. It's allowed. Okay, so we need to adapt that. So 2N mole of NO2, for example, per unit time. Okay, right. So this is true. Why? It is true because N mole of N2O5 forms, in other words, N mole of N2O5 forms 2N mole of NO2 per unit time. And therefore you can see whenever this is 2, this one is double this. 2 times 2 is 4. Right, so yeah, that is the reason. That is the reason. That is the reason. Okay, so yes, indeed, it is true It is true that the rate of decomposition of N2O5 gas is half the rate of formation of NO2 gas. It is indeed true. For 2 marks there, we're done. Move to the next question. Move to the next question. Okay. Consider the following decomposition reaction that takes place in a sealed 2 cubic decimeter container. Right, and you have that the N2O5 breaks down to NO2 plus O2. The graph below shows how the concentration of N2O5 and NO2 change with time. Calculate the mass of NO2 present in the container. Calculate the mass of NO2 gas present in a container. In the container at 400 seconds. Let's take a look at the graph. Let us take a look at the graph. At 400 seconds, here we are at 400 seconds. We're here. Okay, I know that it must be exactly on this thick line here, like so. And then we are asking the question. We're asking the question. We want to calculate the mass of nitrogen dioxide gas present in the container at 400 seconds. Remember that nitrogen dioxide is one of the products, as much as oxygen is also one of the products, right? And so the question then is, what exactly is the mass here? So the couple of things we're able to see. Remember that we actually said that the concentration of the NO2, being the concentration axis, this one in moles per cubic decimeters, we can see the concentration increases. The concentration begins from the origin. In other words, we begin with 0 concentration. We did not have anything at all in terms of what the NO2 was. There was no product in the beginning when the entire chemical reaction began. But now let's look at 400 seconds. We need to calculate now. At 400 seconds, for example, now we want to calculate the concentration, or rather the mass of NO2 present. Now, what do we have? We have the concentration. What is at 400 seconds? Time is in seconds. At 400 seconds, we go to the graph of NO2 gas. And what do we see? We see 200. 200 cubic, but it's 200, but it's times 10 to the power minus 4 moles per cubic decimeters. Okay. But what exactly are we able to extract from the graph? We're able to extract time in seconds, 400 seconds, but also the concentration, right? The concentration of NO2, which is exactly 200, but everything is multiplied by 10 to the 4th power. Concentration. Concentration, 200. Times 10 to the minus 4. Okay. That is the concentration, but yeah, the time is 400 seconds. We know that. But we want to find the mass. So it's easy. And when I say concentration of NO2 gas is mass over molar mass. What is the concentration? It's 200 times 10 to the minus 4 equals the mass. What is the molar mass? Okay, you can do the molar mass times volume. Molar mass, molar mass times volume. The concentration is mass over molar mass times volume. Because we know that number of moles is mass over molar mass. And we know that concentration is number of moles over volume. So now number of moles is mass over molar mass. You put the mass over molar mass in the n place, in n's place, and therefore you have mass over molar mass times volume. Right, we have exactly the situation. Right, the question then is, what is the molar mass of N2O5. So, right, we're going to do the molar mass of NO2, yeah? Okay. Now, the molar mass of NO2 is straightforward. We need to know what that is. So I'm just going to give it to you now because I did not load the periodic table here. So I'm just going to give it to you because we need to just check in the periodic table. Just give me like a split second. I did not load the periodic table, but obviously we know the periodic table very well. So I want to cite the mass, the actual molar mass. Okay, yeah, I know you know it. Okay, so I know you know the periodic table. So the molar mass, capital M of NO2. Okay, so okay, now for nitrogen, for example, we know very well that nitrogen is what? It has a relative atomic mass of 14. Right, we know that. So it will be the molar mass of nitrogen. And then now you have the molar mass of the two oxygen atoms there. And therefore, for nitrogen is 14. And for oxygen, it's going to be 2 times 16. So this is exactly 14, and 2 times 16 is 32, and therefore this is 46 grams per mole. So that gives us the actual 46 grams per mole, and it gives us the actual molar mass. So we're going to put 46 here. The volume is 2. Right, so it is actually 2 cubic decimeters. And we are in business because yeah, all is well. And then we just solve for M. Solve for M, we cross multiply like this, and we get that the molar mass is actually exactly 200 times 10 to the minus 4, 46 by 2 equals what? 46 by 2 equals what? 46 by 2 equals what? Okay, let's launch our calculator. Let's launch our calculator. You know, calculator becomes as follows, yeah? It's not C. Okay. Okay, thanks, Noah. You said 108. Let's just check. I need to convince myself. Okay, 1.84. All right. I believe you. I believe you. I trust you on this one. 200 times 10. Thanks for trying always. Right, to the minus 4. And then you multiply that by 46. You multiply that by 2. And you have actually, very well done there, 1.84. That is the mass. So we have 1.84. 1.84. 1.84 grams. 1.84 grams. So this is actually what we have. And this is the mass of NO2 present in the container at 400 seconds, right? The next question is now calculate the average rate of production of oxygen in mole per cubic decimeter per second in 700 seconds. Yeah? So now we need to perform a calculation. Is the average rate, calculate the average rate of production, right, of what? Of oxygen. Just that way. And when do we do? They have to do that in 700 seconds. Right, so we're going to do that in 700 seconds. And we continue as follows. Average rate of production of oxygen. Let's do that together. 700 seconds. Okay, let's just check here. This is 200, so this is halfway. It's like 100. This is 200, so it's like 100, 200. Like 100 more, 100 more. So this is going to be 200, then you add 100 more, you get 300. You add 100 more, you get 400. 100 more, 500. 100 more, 600. 100 more, 700. Okay, I'm mentioning that because they are saying calculate the average rate of production of oxygen gas in moles per cubic decimeter per second in 700 seconds. Let's take a look. Right, remember average rate of production of oxygen. We need the average rate of production of what? Of oxygen. So which means therefore, at this point you're going to say 700 production of oxygen. Which graph will be relevant for the production of oxygen? One of the graphs here shows a decrease in concentration. Okay, very well done there. Very well done there, Noor. So you're able to see indeed that the graph that actually shows the formation of oxygen, and oxygen itself indeed is a product, and hence it makes sense to say you begin with zero concentration of oxygen and we expect the oxygen to start building up, right? So in other words, we have the following to say. Right, this is our story. We have the balanced chemical equation here, meaning 2 moles. For every 2 moles of dinitrogen pentoxide, there are 4 moles of nitrogen dioxide forming, and also there is 1 mole of oxygen gas that forms. So now the average rate is the formula we're going to use. We're going to say the average rate. Right, so the average rate. What is the average rate? Right, the average rate becomes the following. Yeah? Want to write a formula here? Becomes change in concentration of N2O5 divided by the change in time. So the average rate of production of oxygen Okay, that's a good question. Why is it negative? Why is it negative? It is negative because we are able to see that the graph itself, if you look at the change in concentration of N2O5, okay, we're gonna use 2 approaches to this. But now, if you look at the N2O5 itself, we really can see that the graph itself appears to show what? Appears to show, for instance, a decrease, yeah? Right, and as it shows a decrease, right, it means that even it's the average rate is the change in concentration divided by change in time, and at this point, this graph has a negative slope that we chose. I decided to choose graph B, but we're gonna use also graph A. We're gonna use both graphs in 700 seconds, and we're gonna get exactly the same answer. But now I decided I'm gonna use graph B, whose slope is negative because it's running down slope. This one is running up slope, so this one is running down slope, and therefore it is negative. Very well done there, Noah, for obviously making that observation. But okay, let's take a look. Okay, because it is running down slope. It is running down slope, right? Because it is running down slope, we put a negative. Why do we put a negative if it's running down slope? Because it is running down slope. And if it's running down slope, then the gradient is negative. So in other words, the average rate becomes what? Becomes negative. But we don't want a negative average rate. So we must put a negative in front like this to make sure that we have negative times negative in the end, which is become what? Which is become a positive average rate. Because when we see the graph is running down slope like this, We need to put a negative in front because the answer we're going to get is going to be negative, but we'll then multiply it by negative to get a positive. But for this one, we're going to use also, we're not going to put a negative here because this one is running upslope. So the slope, the average rate is already positive there. So yeah, the gradient, the slope is positive. So we don't have to put anything. Okay, yeah, we are on point. Pay attention. So now we have the average rate. Right, so that in the end, what is the change in concentration of N2O5? What is the change in concentration of N2O5? Now let's check. We decided to, I decided we're going to choose B. Okay, we're going to use A also. But B is showing a decrease in concentration, meaning that we can see that it is our reactant that is undergoing what? A decrease in concentration. So now we've put a negative because the slope is running down slope. The graph is running down slope. Its gradient is negative. But we need a positive average rate, so we must put a negative so that we'll have a double negative giving us a plus. But moreover, what is the slope in 700 seconds? Let's take a look. Right, so in 700 seconds, we are here at 700 seconds, and we are able to see a couple of things. Okay, this is 50, so we need to read this one, right? And this one, the time is 700 for graph B, but okay, we can use any of the graphs because this is a chemical reaction. So yeah, the rate compares for the products and the reactants. The rates compare, right? So now we then say, okay, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just counting the lines. So you can see there are like 10 faint lines between two bold lines, between every two bold, like between every two thick lines. The thin ones are like 10. So they're like 10 steps. So then you must then say 50. You can say 50 minus 0, you divide by 10. 50 minus 0 divided by 10 to get the step. So you then say 50 divided by 10 is 5. So meaning each of these is 5, 5, 5, 5, 5. So when you get to 50 here, this one is, if you check very carefully, it is exactly at 1, 2. 1, 2. Meaning that it's 10 more than 50, giving us a 60. Giving us a 60. So we shall then say the concentration here is going to be what? So there is a point like this of the graph that is going down, and it's going to be at 60 times 10 to the minus 4. Okay, that is the y. It's okay. That is the y. And then the x is the time, 700, yeah? Because the time is on the horizontal axis. We have the time here and we have the concentration there. But now we have exactly this. Okay, so let us do this. Okay, we check that. And then we can check another point. To find average, you must check 2 points. 2 points. So we can do this one of the 700, but also you can choose this one. Okay, what are the coordinates of this point at 200? So x is what? X is naught. And y is this one, which is 200 times 10 to the minus 4. Right? So 0, 200. Okay, so we're back. So here, this one is going to be x is 0 and y is 200 times 10 to the minus 4. 200 times 10 to the minus 4. Okay. So yeah, we have this here. So this thing here is a change in concentration. So one way to do this is to then say, with this point initially at time 0, at time 700. So you can look at the things like, okay, what is this? x1, y1, x2, y2. We use the thing we use in analytical geometry. Slope is y2 minus y1 over x2 minus x1. Change in concentration, yeah? So the concentration is going to be like a y2. What is the y2? It's 60 times 10 to the minus 4 minus y2 minus y1, 200 times 10 to the minus 4, all divided by the change in the time. Okay, whenever you have 60, 60 goes with 700. Minus. So you have 700 minus x1, 0. And we're going to use our calculator here. Let's use our calculator very quickly. Okay, here's the calculator. So that at this point, we have, if you want, you can put already a negative in front, like this. And then you do this, then you do 60 times 10 minus 200 times 10 times 10 to the minus 4. Okay, let me put a minus 4 like this, divided by 700 minus 0, like so. So we get 1 divided by 50,000, which is 2 times 10 to the minus 5. 2 times 10 to the minus 5. So you have 2 times 10 to the minus 5. The average rate is going to be, the concentration is given in what? Vertical axis. In moles per cubic decimeters per second. The per second is going to be extra. So this is in moles per cubic decimeter per second. But this is not the answer, because this is just the average rate, and we use the N2O5. But in view of the reaction, how does the N2O5 compare to the production of oxygen? Double. N2O5 is 1 of oxygen. So meaning the rate. Meaning when I say the rate, the rate of oxygen. The rate of oxygen is 1/2 the rate of oxygen is actually what when compared to this N2O5? It's 1/2 the rate of N2O5. So when you take the rate of N2O5, you multiply it by 1/2, you get 1. In other words, multiplying 2 by half gives 1, which is equal to that of oxygen. And simultaneous, this is 1/2. What is the average rate of the N2O5? Is 2 times 10 to the negative 5. What is 2 times 2? 1 times 10 to the minus 5 moles per cubic decimeter per second. Per second. Per second. And this is the answer. But like I said earlier, this is not the only way. Here we used graph B. We used the graph B. We used the graph B, this graph here. Graph B, this graph that runs down slope. But we can use graph A. because now we can see there's an increase in concentration. We can think there's increase in concentration of the substances, but obviously we said this graph A is going to show it shows an increase in the NO2 concentration. Right. So we continue. Look, let's use graph A now to do the same thing. To calculate, to do this question, because you can use any of the graphs. So you're gonna use graph A to do this. But you see, let's look at graph A. So graph A is sort of an increasing sort of graph. But now it's gonna get to the 700 seconds. Okay. It's gonna increase like this. It's gonna get to the 700 seconds. This graph. But when you get to the 700 seconds, you've already seen that these things are like 5. So that, okay, we continue. So here it's 1, 2, 3, 4, 5, 6. 6 times 5. What is 6 times 5? It's like 30. It's like 510. Yes. Okay, that's a good question. Can you leave the answer as a fraction? Yes, obviously, you can leave the answer as a fraction, yeah? You can leave the answer as a fraction. It's correct. Like 1 over the 50,000 we got. Got something like 1 over 50,000. So you can leave your answer like that. But here it's 5, 10, 15, 20, 25, 30. So if this is 250, yeah, definitely you can leave it as 1 over 1,000, yeah? Can leave it as 1 over 1,000. That's okay now. Right, so now I want us to do this one. To then say this one here at 700, it's going to be 250 plus 30, giving us exactly 280. So this is 280 times 10 to the minus 4. That is what we have here. And then we're going to have something here. We can include the origin, 0, 0, because we're dealing with the graph that starts from the origin, and the graph that begins from the origin is the graph A, and it has to do with what? It has to do with actually nitrogen dioxide. Okay, so we're good. Let's do that one. So yeah, this is the graph for nitrogen dioxide formation, which is one of the products. Now let's do this. So it means that we're going to use this graph. We expect to get the same answer, but this graph here is essentially the graph from the origin. Please, people, it's graph A. That's what it is. It is exactly graph A. Like so. Then what is the average rate? We can write average because there's no time in the exam, so you can just write average. You need to train yourself. We need to do a lot of training sessions on writing. We need to do that now. We need to do writing exercises. We need to start doing writing exercises to see how much time you can take to do these questions because, yeah, it's not easy to finish. Okay, so which means therefore we're going to do the change in concentration divided by the change in time, and this is the average rate. But now we write of rate. What is the change in concentration? So it's going to be exactly 280 times 10 to the minus 4 times 10 to the minus 4, which is this one minus 0, divided by change in time, which is 700, minus 0. Okay, yeah, because this graph starts from the origin and it ends there. And we just need to choose 2 points on the graph, but you can also choose some intermediate points. possible to choose like some points in the middle. So now, okay, look, here we did not put a negative. Why? Okay, we need to discuss that. We did not put a negative, but in the first case, we put a negative there. But now we did not put a negative on this graph that is running upslope from the origin, and this graph increases, showing an increase in concentration, and we did not put any negative in the calculation of the average rate, and we have to discuss the reason why. Okay, so we have -4, -0, and you divide by 700 -0, like so, which is 4 times 10 to the -5. 4 times 10 to the -5. Right, we're getting 4 times 10 to the -5 moles per cubic decimeter. The concentration is moles per cubic decimeter, and in the beginning we have the time in seconds, so it's per second as well. So it's moles per cubic decimeter per second in the 700 seconds. Then, obviously, when you get to this point, you'll be like, what is this? Because here the average rate was 2 times 10 to the -5. Now you get here 4 times. Is it correct? Yes, it is correct. Because we know that the rate of oxygen and NO2. If you want to find the rate of oxygen, you need to, and you have the average rate of the NO2, you need to say 1/4 of the rate of NO2, which is 1/4. What is the NO2? Right, the average rate of NO2 is this one, which is 4 times 10 to the -5 moles per cubic decimeter per second. And this is 1/4 times 4, giving us 1 times 10 to the -5 moles per cubic decimeter per second. And this is the answer, because we wanted the average rate of production of oxygen in moles per cubic decimeter per second, and this is 1 times 10 to the -5. But also here, it is 1 times 10 to the -5. 1 times 10 to the -5. So there it is. Right, so this is the question we just solved now. So the average rate of production of oxygen gas is 1 times 10 to the -5. But you see, we got the average rate. The way we did the average rate here, we put a negative in front. We put a negative before so we said negative is the change in this. Why did you put a negative here when we use N2O5? Because we saw that with N2O5, that is this one here, we saw that this N2O5 has a negative slope, has a decreasing gradient, sort of a decreasing function. So because it's decreasing, we're able to see, we need to put a negative into the average rate. Here we need to put, we put a positive anyway, because it is running upslope. Okay, and so that is the fundamental reason. So, but also here we did not put anything. There was a plus, if you like, and the answer remained positive. So this is a clear indicator of the fact that we need average rate that is positive. We move forward. Okay. Now there's something called the Maxwell-Boltzmann distribution curve for the N2O5 gas initially present in the container is shown below. This is the Maxwell distribution, Maxwell-Boltzmann distribution curve for the N2O5 initially present in the container is shown below. The initial concentration of N2O5 gas is now increased. So remember, this is the Maxwell-Boltzmann distribution curve for the N2O5 gas initially present in the container is shown below. Remember, N2O5 initially present in the container. This is the graph. The initial concentration of N2O5 is now increased. Somebody says, hang on, it is there, but it's being increased. Redraw the distribution curve above in the answer book and label this curve as P. On the same set of axes, sketch the curve that will be obtained for the higher concentration of N2O5. Label this curve as Q. So I need to draw two curves here, but on the same set of axes. Yeah, on the same set of axes. So this is what we're going to do. Right, 5.4.1. So we're going to do this. This has to do with the kinetic energy. And this one is the number of particles. Number of particles. The P curve. So draw this one, P. Now, the concentration is then increased. So if you increase the concentration, you increase the number of the particles. If you increase the concentration, you increase the number of the particles. And this curve is going to be curve what? Curve Q. So now, this is the situation. So if you look at the number of the particles in curve P, this is what you have. But now, if then you come and then say the initial concentration is now increased. Somebody says, you know what? Okay. All right. Okay. The equation. Remember, this is the equation. This is the equation. The equation is that 2 times N2O5 is 4 times NO2, the oxygen. Right, so you can write it here. 2 times N2O5 is what? It's 4 times NO2 plus oxygen. Right, 4 times NO2 plus oxygen. Okay, this is the equation, and these entities here, these substances are in gaseous state. So that in the end, we have what? When we increase, right, we decide to increase the concentration of N2O5, and what then happens? The number of the particles increases. And when the number of the particles increases, we're able to have more. This graph, therefore, is going to be higher, and the other one is going to be a little bit less. Okay, yeah. So that is something that, okay, why is the graph on top, right? That's the question. Why is the graph at the top? The graph is at the top because they're saying now in the new graph, this is the original one. This one, graph P is the original one. But now, if we increase, we decide, you know what, we're going to increase the concentration of the N2O5. We're going to increase it. When it increases, what happens? Then the number of the particles increases. Because by definition, concentration is number of moles of gas over volume. Concentration is number of moles. Like it relates to the number of the particles per unit volume. Number of the particles per unit volume, that defines the concentration. It's like pressure, this. So in the end, then we then say, if the number, this is the number of particles on the vertical axis. But now if we then say the initial concentration of N2O5 is now increased, then what happens to the graph? The graph, therefore, will experience more particles. Number of particles increases. When the number of particles increases, we have that the graph is not going to have the same number of the particles. Because whatever the case, if there were 6 times 10 squared, okay, if there's 6 times 10 to a number squared, then here now, so 6 times 10 to the 24, Suppose something like that. Okay, that's reasonable. And then now if you increase it, then the more. The more. So you have like 12 times 10 to the 24. Yeah? So there's an increase. There's an increase. The number of the particles is greater and the graph must be above. The graph must be on top. The examiner wanted to catch the students because now this is that you don't have specific numbers. So because you don't have specific numbers, the examiner wanted you to draw the original one and draw the other one to see if the student is going to draw it on top or it's going to draw it at the bottom or it's going to intersect the graphs in some way. Okay? Yeah, something that you need to like take a look at. Think about it. Give it some tough thought. Next question. 5.4.2. The initial concentration of N2O5 is now increased. Will the rate, so if this is actually right, 2N2O5, 4NO2, O2. 2N2O5, 4NO2, and oxygen. Gaseous state. These are all gases. And we're then saying the initial concentration of N2O5 is now increased. Somewhat increases the concentration of N2O5. Will the rate of decomposition of N2O5 at the higher concentration be higher than, lower than, or equal to the original rate of decomposition? Explain the answer using collision theory or using the collision theory. Yeah? What's the answer here? What's the answer? So what is the examiner saying here? The initial concentration of N2O5 is now increased. The initial concentration of N2O5 is now increased. Okay, yeah, let me see what Noah is saying. Okay, that's fine. Noah thinks it's going to be higher. Very well done, Noah. It's going to be higher than. It's going to actually be higher than. Right. Right. And now they're then saying, explain the answer using the collision theory. First point is that when the concentration of N2O5 is higher, when the concentration of N2O5 is higher, there are more N2O5 particles per unit volume. When the concentration of N2O5 is higher, there are more N2O5 particles per unit volume. That's the reason. Next, it's higher than because then we have more effective. With more effective collisions. More effective collisions per unit time. More effective collisions per unit time or per second. More effective collisions per unit time or per second. Yeah, think about that one. Right. Simultaneous, you can then say if higher frequency. Higher frequency of effective. Higher frequency of effective collisions. Higher frequency of effective collisions. Higher frequency of effective collisions. So we get back to the question for the 3 marks to see exactly what needs to be answered here. Okay, let me see what Noah is saying. Does decomposition mean using up? Yes. Well, decomposition has to do with using up, but after decomposition is like breaking down. So the rate of decomposition of NO2, why is the examiner using the word decomposition than the word, using up, for instance, or being used up, or whatever? Right. The examiner is using the word decomposition because, so in terms of the choice of words, the word is sounds more appropriate because the N2O5 breaks down. Produces breaks down to 2 chemical substances. Because it breaks down to 2 chemical substances which are different, yet these substances are both gases, and we then say it is therefore breaking down. And breaking things down in science and mathematics, we say it's decomposition. So it's a breakdown because now it's breaking down to 2 pieces. Just 1 piece, but now it's like 2 pieces. So the word decomposition, you can say it's used up. It's used up. You can say this is used up, but when it's used up, the N2O5, the dinitrogen pentoxide, it's used up then to form NO2 and oxygen. Okay, right. So the initial concentration of N2O5 is now increased. What is happening in this case? The initial concentration of N2O5 is now increased. Somebody increases the initial concentration of N2O5 of this guy. Will the rate of decomposition of N2O5 at the higher concentration be higher than, lower than, or equal to the original rate of decomposition? Right. Explain your answer using collision theory. We said the rate is going to be higher than. Why would it be higher than? It will be higher than because, right, it will be higher than. So higher than will be a mark in the exam. When the concentration of N2O5 is higher, there are more N2O5 particles per unit volume. When the concentration of N2O5 is higher, there are more N2O5 particles per unit volume. That is reason number 1. Number 2, more effective collisions per unit time. Because there are more particles, more N2O5 particles, then there are more effective collisions per unit time. And if there are more effective collisions, then it means that then you would have the rate of decomposition is going to be faster because there are more effective collisions because of the higher N2O5 concentration there. Okay, so think about that one. Make sure you understand it. Move on. Question 5. Right, so now let us look at question 5. And this is the question 5 we're going to do just now. But it's a very, very interesting one. And it is awesome, 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 awesome. Right, now let us look at this question and make sure we understand it. And make sure that we actually can be able to solve this particular question together. Right. This is extremely, extremely important for us. So let's take a look at this. If there's a flask that is in front of us, and let's note.
Thiosulphate.
Right. So in other words, the reaction between excess. Right. So the reaction between excess dilute hydrochloric acid and sodium thiosulphate is used to investigate factors that influence reaction rate. Sodium thiosulphate and hydrochloric acid react and yield sodium chloride, sulfur, water, and your sulfur dioxide. Okay, so you have your sulfur, you have your sulfur dioxide. If you sodium chloride, your salt, etc. In aqueous state, this and this is a solid, etc. This water, it's a liquid, and the SO2, it's a gas. The concentration of hydrochloric acid used is 1 mole per cubic decimeter. The same value of HCl in aqueous state is used in each run. The time taken for the cross on the paper under the flash to become invisible is measured. Okay, so we're reacting these two things here, and we're reacting the sodium thiosulphate and also the hydrochloric acid of known concentration, 1 mole per decimeter cube. Do you know that if the concentration is known, this is of particular importance to us? Okay, we're going to discuss that in a little bit of time. So now the time taken for the cross on the paper under the flash to become invisible is measured. Thiosulphate. Right. So now they measure the time taken for the. Okay, it's a very interesting experiment, this, because now when you react these two things, at some point you can see the cross, at some point you won't see the cross. The table below summarizes the reaction conditions and results of the experiment. You have run 1, run 2, run 3. Run 1, 2, 3. Then there's volume. The volume is sodium thiosulphate, aqueous state in cubic centimeters, 50, 40, 30. You can see a decrease in the volume from 50 to 40 to 30. But look, the volume of the water in liquid state added to cubic, in cubic centimeters, it's 0 water, and then there's 10, and then there's 20. So the volume of the water is doing what? The volume of the water is actually exactly showing an increase. I want us to discuss this at length as follows. I want us to discuss these at length as follows. Okay, so let's write something here. Na2 S2O3 aqueous. 2HCl aqueous. 2NaCl aqueous. Sulfur solid, water. H2O in liquid state. Sulfur dioxide, gas. The table below summarizes the reaction conditions and the results of the experiment, right? So we have run 1, 2, and 3. Then volume. Volume increases from 50 in run 1, run 2 is 40, and run 3 is 30. So you can see a decrease by 10. 50 minus 10 is 40, subtract 10, get 30. The volume of water increases. The concentration itself, it was, okay, so you can, the volume of the water is 0, then it's 10, then it's 20. Then the concentration is 0,13, 0,10, then P. The time in seconds is 20,4, 26,7, 33,3. Okay. Define reaction rates. Define reaction rate. Let us define reaction rate. Let's take a look at this. What do we mean by reaction rate? What do you mean by reaction rate? 5.1. Right. So now this is just 2 marks. So you can then say that it is change in concentration of products change in concentration of products or reactants per unit time. Per unit time. Right. Okay, continue. What is reaction rate? Change in concentration of products or reactants per unit time. If you don't want to say it like this, it's refers to the amount of moles. Amount of moles. Or you can say, right, can say amount, number of moles of volume or mass of products formed. The amount or number of moles, volume or mass of products formed, or reactants used. Reactants used. What is reaction rate? Another student can come and then say here, it is a rate of change. Rate of change in concentration. Rate of change in concentration. Okay, so reaction rate is not only defined in terms of concentration. So we can say rate of change in concentration or rate of change in amount. Okay. Okay. All right. So the rate of change in concentration, or amount or number of moles okay. Okay, that's fine. Okay, good. So yeah, I understand that. But I wanted to emphasize this definition. It's a very, very important one. Right, it's a very, very important one. Volume, volume or mass. Okay, this last definition is very, very important because it gives us the formula for reaction rate. So the rate of change in concentration, what is reaction rate? Rate of change in concentration, or rate of change in amount, or rate of change in number of moles, or rate of change in volume. So the rate of change relates to concentration, like we've used, number of moles, volume, or the mass. Move on. 5.2. Okay, 5.2 is this one. Write down the independent variable of this investigation. Write down the independent variable of this particular concentration. Which one is the independent variable? Right, independent. The independent variable is the variable we change. What variable are we changing? So you'd remember in the beginning, the reaction between excess dilute hydrochloric acid and sodium thiosulphate is used to investigate factors that influence reaction rate. The concentration of the hydrochloric acid used is 1 mole per cubic decimeters. The same volume of HCl is used in each run. The time taken for the cross on the paper under the flask to become invisible is measured, but the same volume of HCl is used in each run. So in each run, the same volume of HCl is being used. But let us look at what is happening. Right. Okay. Let's look at what is happening. Right. Okay, let's. Write down the independent variable for this investigation. Write down the independent variable for this investigation. Okay, right, let's take a look. Now, if you check carefully, you're able to see that at this point, the concentration was 0.13. Then the concentration becomes 0.10. And then the concentration becomes something P. But also the times here themselves increase this way. So at this point, it is clear that in 5.2, concentration is the independent variable. Concentration of Na2S2O3 Okay, we continue. Okay, so concentration of Na2S2O3. So the concentration of the sodium thiosulphate, it's the one that is actually obviously being changed here. Because you're able to see that this is sort of a standard solution in which the concentration in which the concentration of the HCl, the concentration of HCl used is this one. So it is clear that the HCl's concentration does not change. But now you are changing the concentration of what? Of Na2S2O3 sodium thiosulfate. So the concentration of the Na2S2O3 is the one that is being changed, because we are combining two things here. We're reacting sodium thiosulfate and HCl, and we're able to see, okay, the HCl, its concentration is it's 1 mole per cubic decimeter, and we're just changing the concentration of this until such time that obviously the cross becomes invisible, so that we don't see the cross anymore. Calculate the value of P. Next, calculate the value of P. Calculate the value of P. Let's check. Yeah? Okay. Right. I was saying here, in this case, they want us to write down the independent variable. How do we see the independent variable here? Because we just have this flask here. But this flask that is in front of us is undergoing a couple of runs. Okay? Undergoing a couple of runs. But whenever we do a mixture, a chemical reaction of the sodium thiosulfate and HCl, we make sure that we have 1 mole per decimeter cubed, or per cubic decimeter, of concentration of the HCl. Now the question is, how do we see the independent variable in this case? Okay, the HCl is fixed, doesn't change the concentration, but we continue to use this particular, flask, such that in run 1 we combine the volume of the sodium thiosulfate is this. In run 2, this is the volume, less. In run 3, the volume itself is what? It's a little bit less. But it is still sodium thiosulfate. Now, what actually is going to lead to the cross disappearing? What is it? Because in effect, we're reacting two things here. We're reacting HCl and the Na2S2O3. So clearly, it is this one is fixed at 1 mole per decimeter cube, and therefore this one is the one whose concentration is changing. It is our hope that we want to know how much time it will take up to run 3 to make sure that we don't see the cross anymore. So we have 3 runs. In the 3 runs, we actually have 1 mole per cubic decimeter of concentration of the HCl, and then this one, we vary its concentration. So we vary the concentration of the sodium thiosulfate, right? And when you do that, we want to see the time it takes for the cross to disappear, such that when we look like this, we don't see the cross anymore, so that the cross is gone. That is our wish, so that the cross disappears, okay? Okay, calculate the value of P. Let's find the value of P. So yeah, they were asking us to write down the independent variable. It is concentration of the sodium thiosulfate. Okay, we'll continue. We continue. We continue. Right, so we continue. We continue. Right. So now, you then say the table below summarizes the reaction conditions and results of the experiment. Calculate the value of P in the table. Calculate the value of P in the table. Calculate the value of P in the table. So we continue. We continue as follows. We continue as follows. Right. So how do we find the value of P in this table? How do we find the value of P in this table? Let us find the value of P in this case. Right, we continue as follows. Okay, let us look at this table and want to find the value of P in this table. But how do we do that? Right, a couple of things we need to know. That concentration is number of moles over volume. What is the concentration? Like in the first run, the concentration was 0.13. Was 0.13. The number of moles are the ones we need to get. And then now we'd have to determine the volume. Right. And when we actually have the concentration of 0.13 of this, what then becomes the volume? And we need to convert the volume to the cubic decimeters. Right. So let us check this out. We need to check this out. Okay, we pause for a minute. So now we do the following. Right. We'll do the following. Right. So in this case, if you already know, for example, the concentration of the HCl was this. Right. Right. Something I want us to do here. Something I want us to do. Okay, take a look at this and reason with me, please. Take a look at this and reason with me as follows. Right, we want to find this guy, which is the concentration P. And we have already said, we've already mentioned that concentration itself is number of moles over volume. And we can see the concentration, for instance, in the beginning was 0.13. Now, when the volume of the sodium thiosulfate was 50. So I want us to use a calculator here. I want us to use a calculator and perform a couple of calculations. Like if you have the 50 And if you divide it by okay, right, but also you can see there's a change in the volume. So it's going to be sitting at this point. Whenever we have P, the volume is going to be sitting at exactly this point, yeah? Okay, so we're good. Meaning the volume itself, you take the 30 volume of the Na2S2O3 aqueous is 30 divided by 1,000, 0.03 cubic decimeters, yeah? Check this out. Right. So you have the 30 divided by 1,000. 0.03. 0.03, yeah. So you're going to put 0.03 so that now the N 0.03. So that you have the 0.13 times 0.03. Yeah. 3.9 times 10 to the minus 3. 3.9 times 10 to the minus 3. 3.9 times 10 to the minus 3. Moles, yeah? Because it's N moles. Like so. So now we are able to see, like in the first run, we had that the concentration was 0.13. And then we have the number of moles and the volume. At P, the volume was 0.03. Okay. So that's a good question. Why didn't we use 50? Because we're interested in the concentration at P. Now, the concentration P has volume 30 cubic centimeters. Right, and so okay, think about this. Let me see what. Okay. Okay, right. Right. Okay, there are a couple of ways, obvious, to do this particular question. Because you have different concentrations and hence different volumes that are involved. But we are really saying in the beginning when we did run one, the concentration was 0.13 when the volume was 50. Now we reached a time when the volume was 30 And we're interested in finding the concentration P. Right. I want us to use this following approach as well. Something I want to show because this one is it's much easier and it's much of a shortcut. Okay, there's another formula we use that says, for example, C1, you can write here, C1 V1 equals C2 V2. Okay, let's use this one. C1 V1 is C2 V2. Zero comma 1 3. 0 comma. Okay, now would come and then say, for instance, if we then say C1 concentration 1 volume 1, and then concentration 1 we take 0 comma 1 3, and then we consider volume 1. Right, and when we take the concentration of this one here with the volume 1, and you consider volume 1 to be, if you have these 30 and you divide it by 1,000, you get 0.03. Then we have concentration 2, which you can call P if you want. And then there is volume 2, this one. Right, so you have concentration 2, and then you have volume 2, and volume 2 is what? Is the 50 divided by 1,000, getting 0.05. Okay. So look at the fact that here we have concentration 1, volume 1. Yes, we cross multiplied. So we cross multiplied because we have concentration 1, which is 0.13. We relate it to this particular volume, which is then in turn call it volume 1, which is 0.03. And then we say there is concentration, this one, which relates to the P. Right, and then if you continue with that, which means P is the same as what? 0.13, 0.05. Okay, then let's use a calculator just to check the answer here. Zero 0.13 times 0.03, 0.05. So getting 0.078. 0.078, and therefore this one gives us a concentration in moles per cubic decimeters. Yeah, we use ratios, yeah? Use ratios. We use ratios to do this. So in the same way, so we use the notion of ratios. So now, with this mentioned in the same way, so you switch this around. Right, so obviously now you use the 0.13 concentration. 0.13 concentration deals with the 0, 0.30 volume, 0.03 volume. And then we get the number of moles. If you use concentration equals number of moles over volume, then you get this. It is 3.9 times 10 to the minus 3. Then in turn, okay, because we need the value of P, so what is the value of P? Would use, therefore, the fact that concentration is number of moles over volume. Right, so it's our P, which equals, what is the number of moles? We've already got the number of moles, which is 3.9. 3.9 times 10 times 10 to the minus 3, divide by the volume. What exactly is the volume? So the volume now, if you're at P, then use this volume. So you divide by 1,000, you get 0.05. And then you're going to use a calculator. Let's use a calculator quickly. Which is 3.9 times 10 to the power minus 3. Divided by 0.05. Which is 0.078. 0.078. 0.078. 0.078. Yeah, because it's concentration. Concentration is what? Is in moles per cubic decimeters. Okay. Which is 0.078 moles per cubic decimeters. Okay, so that is the value of P. But we used two ways to do it. If you want, you can use C1V1 equals C2V2. So use the notion of ratios to do this. Use the notion of ratios to do this. You can think about it in many ways, because, yeah, use ratios because I can see that maybe it's like we are switching things around and you'll be like, okay, but why didn't you use 50 with this? But we use the notion of ratios because of the fact that if we use ratios, C1V1, then you switch the things like that. Just try to make sense of that. But yeah, we can always have different ways to look at how these ratios can be equal to each other. Because you can also come here and say, if I'm to do it in blue color, you can write these things in terms of ratios. You can like say C1 over V2 is C2 over V1. So if these two ratios are to be equal to each other, so if you take concentration 1, then it goes with this. Then the 50 goes with that. Okay, think about it. But those are the ratios we use. Next. 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 The table below summarizes the reaction conditions and results of the experiment. The table below summarizes the reaction conditions and results of the experiment, yeah? When 0.21 grams of sulfur is formed in run 1, okay? the cross becomes invisible. Calculate the average reaction rate with respect to sodium thiosulfate in grams. Average reaction rate. Average reaction rate. Average reaction rate. Okay, let's look at this question and reason together. So now we are told that 0.21 grams of sulfur is formed in run 1. Number of moles of sulfur. It's mass over molar mass. What is the mass? Right, it is 0.21 grams. Right, for sulfur, the molar mass is 32 grams per mole. For sulfur, the molar mass is 32 from the periodic table of the elements. From the periodic table of the elements. So, zero 0.21 divided by 32. Okay, let's check what we're getting here. Shall we use a calculator quickly? 0.21 divided by 32. Yeah, let's just use the calculator together. Right, let's do 0.21. Divided by 32. Right, we're getting this one here, which is 6.56. 25 times 10 to the minus 3. 6.56 times 10 to the minus 3. And so now we have, because we know the molar mass from the periodic table of sulfur, which is 32 grams per mole. Calculate the average reaction rate with respect to sodium thiosulfate. So we want, but let us look at the chemical reaction that is part of this question. Right, if you look at the chemical reaction that is part of this question, we know something. We know that Na2 H2O3 in aqueous state plus 2 HCl aqueous two NaCl aqueous plus H2O liquid SO2 gas. So the sodium thiosulfate and the HCl added together, they produce sodium chloride. And, we know this chemical equation. That's what was given in the beginning for this. It was given for this question. So in 5.4, the number of moles here, the number of moles of sulfur would be the same as the number of moles of the sodium thiosulfate because it's 1, 1. And we want to calculate the average reaction rate. Calculate the average reaction rate. Right. When you calculate the average reaction rate, we proceed as follows. Check this out. So what we're going to do is that we already know some things, like you already know that the number of moles of sulfur is equal to the number of moles of Na2S2O3. Okay, because it's 1:1. Yet we have been given for sulfur, so we want to calculate the average rate of reaction with respect to sodium thiosulfate in grams per second. So it is exactly this one. And now this is 6,56 times 10 to the minus 3. Number of moles of Na2 S2O3 is given by what? So number of moles is mass over molar mass. And this means the number of moles of the sodium thiosulfate is 6,5. What is the molar mass? 158. So that in the end, then the mass so now here you'd find the mass. So the mass is going to be cross multiplication. So you cross multiply here. Let's do the cross multiplication here. And do 6.5 times 10 to the minus 3. Times 158. So the mass would be, let's check this out. About 1.03. Okay, you can do, okay, this one can do 0.21. Accurate number of moles here, so you can use the accurate one here. Yeah. And then divided by 32. Times 158. Yeah, it's 1.04. Accurate answer. 1.04. So the mass of the sodium thiosulfate is 1.04 grams. 1.04 grams. Yeah. Okay, check this out. Okay, I'll check your messages there, Noor. So this is going to be exactly 1.04 grams, yeah? Okay, yeah, I get you. Yes. Yeah, I got 1.03, but just that we rounded off this one, you know? We rounded off because when divided the 0.21 by 32, we got 6,56. So, yeah, but you'll be marked right as well in the exam. You'll be given marks, full marks for that, but just a discrepancy. It shows that by rounding off, we can get some answers that a little bit different. But now you're able to see that if we use 0.21, 32 times 158. Right, we get 1.04, so you can still get 1.03. It's pretty acceptable, but 1.04 is the most accurate answer. Okay, so the mass of the sodium thiosulfate, therefore, is this one, 1.04. But this is not what we want. What actually do we want? We want the average rate. We want the average rate. So that in the end, you can then say the rate. The rate is change in mass, change in time. What will the change in mass be? The mass is going to be 1,04 grams. You divide by the amount of time, which should be what? Which should actually be exactly 20,4. Okay, use a calculator to find the, okay, but this rate is nothing other than the average rate. So that in the end, okay, yeah, I'll check here the your message then over. So that's gonna be 1.04. You divide by the change in time, which is 20, which is 20.4, which is 0.051. 0.051. So this is going to be exactly 0.051 grams per second. Grams per second. So it means that we can find the mass, and the average rate, excuse, is 0.051 grams per second. Okay, so you have exactly that one there. But yeah, you can write a 0, that. Okay, let me check your messages, Zeno. Okay, that's a good question. What is the initial mass? What is the initial mass? Right, so obviously at this point, remember that we are dealing with what? We're dealing with remember the question says calculate the average reaction rate with respect to sodium thiosulfate, whose mass we know. And what would then be the initial mass? Remember that the concentration of sodium thiosulfate is what? Is changing. And sodium thiosulfate is the independent variable. Its concentration. The concentration of sodium thiosulfate is the independent variable. So that at this point, we started with when we had the sodium thiosulfate, whose concentration was like different. And we kept changing that 0.13, 0.10, then to P. Okay. So in other words, when we started here, in view of the substance we're focusing on, sodium thiosulfate, you'd realize that, or sodium thiosulfate, you'd realize that we started with almost none. And the time in the beginning was naught. So you can always say we started with zero mass. We started with zero mass. And the time in the beginning was 0. Okay, that's a good question. Why 0? Right, it would obviously be 0. For example, you would realize that if you look at this particular way the question was introduced, okay, looking at how the question was introduced, the reaction between excess, so this is excess diluted hydrochloric acid and sodium thiosulfate is used to investigate factors that influence reaction rate. Sodium thiosulfate together with HCl are mixed until you have the products here. The concentration of HCl used is 1 mole. Yes. So it is a limiting reagent because it is a limiting reagent because the HCl is excess. So in other words, the sodium thiosulfate is a limiting reagent or limiting reactant. Right, in which case, therefore, as a limiting reagent, you are able to see that it is the one that will possibly run out. Right, and therefore its mass, okay, good. Then why don't we, okay, so, okay, good. So why don't we do that? We can do that. We can include the fact that since it is a limiting reagent, then ultimately it's going to be used up. Yes, I understand. Okay, right. So there are 0 minus that. So you can use the 0 because ultimately it's going to be used up. So if it's used up, it's going to be consumed completely and we're going to have 0 in the end of it, 0 mass, because there's going to be no sodium thiosulfate in the end because the HCl is in excess. So we can do that. We can do it that way. And then it's ultimately going to have 0 minus this. Okay. So we can do that. But ultimately, no matter what you do, the average rate must be positive. Then the average rate must be what? Must be positive. No matter what you do, you can do it that way. But in the end, guard that your average rate must remain positive regardless of the situation. Let's see. Let me see what. Yes, you say like that. Minus open bracket, 0 minus that, yeah? Like we did before. You can put a minus in front just to guard against this becoming negative, you know? So that would be very, very correct. Let me look at the next question. Another investigation is performed at different temperatures. Okay, so there's another investigation that is performed at different temperatures. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees Celsius. Label this curve as A on the same set of axes. Draw the curve that will be obtained at 35. Okay. Right, so you have those two temperatures. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees Celsius. Label this curve as A. On the same set of axes, draw the curve that will be labeled at 35 degrees Celsius. Label it as B. Remember that another investigation is performed at different temperatures. So another investigation is done, but at different temperatures. So what we need to do is to sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees Celsius. Label this curve A. On the same set of axes, draw the curve that will be obtained at the. So yeah, we have those two temperatures, 20 and 35. So we actually looking at 5.5. So now we have the kinetic energy. And then the number of particles. And then you'd have this one. Okay. Kinetic energy and then the number of the particles. You'd have A, B. So you need to sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees. So this one, A, is at 20 degrees Celsius. B is at 35. Yeah, so what is then happening here? At 20 degrees Celsius, this will be the curve. Right, and also now at 35 degrees Celsius, this will be the curve. Right, you're able to see that when the temperature is higher, then there is more kinetic energy. But when the temperature is smaller, then their particles themselves do not roam a lot. So there's less kinetic energy. There's less kinetic energy. There's less kinetic energy. So this is the situation. Let's move on. Explain the effect of temperature on reaction rate in terms of the... Right, continue. Explain the effect of temperature on reaction rate in terms of the collision theory. In terms of the collision theory. Let's look at this one. Let us look at this one. Okay, why are particles less? Okay, yes, why are particles less? Because you're able to see that for B, the particles will be less, and for A, the particles will be more. Why? Because of the temperature. So when the temperature is very high, that means that there are more potential collisions because the kinetic energy is bigger. Here, the kinetic energy is less at lower temperature. So in other words, at smaller temperatures, at the smaller temperature of 20 degrees Celsius relative to 35, you realize that the kinetic energy is smaller. The kinetic energy is smaller at some time. And here the kinetic energy will essentially be bigger. Why? Because when the temperature is higher, then you have a temperature that is greater, and the temperature directly proportional to kinetic energy. An increase in temperature means favors an increase in kinetic energy, and therefore this graph will widen. And therefore the number of the particles will therefore be such that at 20 degrees, you can view the particles as less. Why? Because at 20 degrees Celsius, the particles do not roam a lot. But here, So now, so you can consider particles rather 20 degrees as more particles. But here, as relatively, because of the higher kinetic energy, the graph flattens. The kinetic energy is very small. Kinetic energy is very small. And if the kinetic energy itself is very small, this graph is sort of pushed towards the origin. And simultaneously, it obviously creates the impression that the number of particles will therefore be not so mobile, not so mobile. And therefore, this graph will be pushed towards the origin. Be pushed towards the origin because of smaller temperature. Smaller temperature means less mobility, less kinetic energy, and the graph is pushed towards the origin, which creates the impression that therefore one has more observable particles relative to the high temperature when the observable particles themselves, okay, yes. So when the temperature is very high, kinetic energy decreases. Rather, when the temperature is very high, kinetic energy increases. When the kinetic energy increases, what does it mean? This is what is actually happening here. So at 35 degrees relative to 20 degrees. Okay, at 35 degrees, what happens? The temperature is very high and therefore they are running a lot. They're running a lot. Right, so if you have that EK is large. Right, and here EK is less. Okay, if EK is large, it actually means a couple of things. Why is EK large? The temperature is higher, and therefore there are more effective collisions, and the particles run around more the container. If they run around more of the container, what would it mean? Then it means that they actually tamper with the space. So they occupy more space, more volume, if you like, more volume, yeah? And here, there will be relatively less volume. So at a small temperature, the volume is small, but at greater temperature, the volume is more. But if the volume is more, then the perception that we get is therefore that the particles are like fewer because the volume is now more. When the volume is more, the particles have more room to play and so on. But yeah, whereas here, at small temperature, the volume is it's because of the relationship between temperature and pressure. Right. What is the relationship between temperature and pressure? Right. Because when temperature increases, all right, yeah, when temperature increases, right, I want to just to remember something about Boyle's law in the first year a little bit, and grade 11. When temperature increases, okay, or let us look at what happens when temperature increases, yeah? When temperature increases, we obviously are able to see a direct relation. So there's pressure and volume, yeah? So there's pressure with volume. So whenever volume decreases, pressure increases. When pressure decreases, volume increases. Volume increases. When pressure decreases, volume increases. So the temperature that is there, if the temperature is a lot, then it means that there is an increase in pressure. And if the pressure increases, the volume decreases. Okay, but obviously this happens at constant temperature. Okay, the Boyle's law case would happen at constant temperature. I want us to, because now the temperature here is not constant, but because the temperature here is changing, right? So it's a different story. But now what then you are then having is that when the temperature is a lot, 35, then what happens? Then these gas molecules gain more kinetic energy to roam around. And when they roam around, because of increasing temperature, they occupy more space. When they occupy more space, therefore, there are like fewer particles in the large space relative to particles here in a smaller space, and therefore, there are like more particles. Okay. Now, if you look at 5.6, okay, explain the effect of temperature on the reaction rate in terms of collision theory. Let us discuss this one. I can see the time, please. At a higher temperature, particles move faster or have higher kinetic energy. At a higher temperature, particles move faster or have a higher kinetic energy. More molecules have enough or sufficient kinetic energy for an effective collision. Okay, let's look at this. At a higher temperature, particles move faster or have a higher kinetic energy. Okay, that's what we said already to explain the difference in the two graphs. But more molecules have enough or sufficient kinetic energy for an effective collision. So we explained the effect of temperature on reaction rate in terms of the collision theory. So these are the 2 points. And now you'll be getting marks like this. Kinetic energy. Right. And the effective collisions. Okay. At a higher temperature, particles move faster. At a higher temperature, particles move faster or have higher kinetic energy. Yeah, that's what we said. More particles have enough for sufficient kinetic energy for an effective collision. And that is what explains the effect of temperature on reaction rate in terms of collision theory. Right, here's the homework. This one is a home activity. Three experiments A, B, and C are carried out to investigate some of the factors that affect reaction rate or the rate of decomposition. Again, it's rate of decomposition of hydrogen peroxide, H2O2 liquid. The balance equation for the reaction is this one. So the hydrogen peroxide breaks down or decomposes into. Right, good, no. Right, so the balance equation for the reaction is this one, which is H2O2 liquid. Once again, this thing is recorded, so I'll send you the recording in a few minutes and then you can see it, you can watch it. Okay, identical samples of hydrogen peroxide are used in each experiment, but we can see that it is a decomposition reaction because the hydrogen peroxide, H2O2, breaks down to water and oxygen. Identical samples of hydrogen peroxide are used in each experiment. The conditions used in each experiment are summarized in the table below. Experiment A, B, C, temperature 25, 25, 35, without a catalyst, with a catalyst, and without a catalyst. In which experiment A or B is the reaction rate higher? Use collision theory to explain your answer for 4 marks. Yeah, I don't like giving a very long homework. So I know there are too many questions that I've planned, but this is enough for today. In which experiment A or B is the reaction rate higher? Use the collision theory to explain your answer. Is it in A, in B, or in C that the what? The reaction rate is higher, right? Because there are a couple of things in A and B, because we're dealing with A or B, but the temperature is the same. It just the catalyst is different. Here there's without the catalyst, there is with the catalyst. Okay, right. I must thank you for joining us. It was awesome having this discussion. We shall have another discussion. We shall talk about when. Right, because you'll have to be free at that time. I need to be free, and then we can have our discussion again. Right. So thank you again, Noah, for joining us. Yeah, I can see the time is just 2:15, and then we'll talk about our next meeting time. Okay, thank you, Noah there, and goodbye. Have a good day. Thank you. Goodbye.